that. Okay, so again, this is a simple model of home air exchange. So this is not a new thing. There are many models and people know how to model indoor air concentrations in the simplest case. So in a single zone, you can write a very simple differential equation that says the change of concentration with respect to time is the source minus a loss term, and that loss term is proportional to how much concentration is in the home because that concentration is getting carried out by an airflow. And there's a volume normalization in here, and I didn't bother to make that explicit, but it's there. And then it leads to a solution that has some exponentials in it. In terms of math, this is relatively simple math. And then you can do that for multiple zones by writing it as a matrix equation. So you write a vector of concentrations and then a flow matrix where you express not only the flow out of each zone, but flows between zones. And I'm not going to dive into the math. It's just like, okay, this is how it's done. And yeah, again, if math is not a comfortable place for you, this doesn't matter because it'll be mainly about the results. But just so you know, this isn't what is considered rocket science in the sort of math engineering world. It's pretty basic. So we already set up a model like that. So we, like many other people, we published a COVID paper that had some of the air quality folks on it. And that model, a simple multi-zone model was used in that paper to describe how virus could transport and could be removed. And so my brilliant idea was, oh, I already have this model. It should not take long to adapt it to the situation. It did take longer than I had hoped or expected, but that's kind of normal. And so some caveats on this model is it's really, really simple. Like you can do fancy numerical things to make it more accurate. I haven't done those. I'm just treating this as a kind of a useful model. And one very important thing is that it assumes that every zone, spelled wrong, a zone is not a new terminology that I'm bringing forward. It's just a zone. It assumes that everything is well mixed. And so there's no lumps of concentration in the middle or on the sides of the room. So you do have to assume that in order for that math to work. So the math is easy, but the hard part is quantifying what the flows are. We've talked about in other meetings how if the outdoor air is colder, you might get flows in at the bottom and out at the top of a house. And that changes depending on temperature differences, wind-driven pressures, mechanical ventilation, and how those all act together. And so you can create a model of how concentration in a room or pollutants in a room would change over time, but what are the values of flow that you plug in? And that's what this part of the project is about. I think you've also heard Dom and perhaps Paul talk about the blower door test. So I'm going to tell you a little bit about how we estimate flows from a blower door test. And Paul and Dom, since I know you've done this, and Paul, you're an expert in this, feel free to jump in and correct me at any time. So what you do with the blower door, which is a giant fan, is you either pressurize or you depressurize the house so that all the cracks in the house are essentially at the same pressure. And then you measure the flow through the fan. And you do that in the fancy test, you do that for a number of different flows. And then you get this flow pressure relationship where Q is a flow, K is some kind of constant, delta P is the pressure across the envelope, which the blower door makes kind of the same over the whole house. And then N is an exponent. And the blower door is always measuring when all the flow across the building envelope is either in or out. And so when we want to do a model under regular conditions, we need to divide the leakage into how much is flowing in and how much is flowing out. Okay, so just an aside, there are many of these simple models, and one of the most famous is called CONTAM. It's a multi-zone model developed by NIST, and they've spent a lot of time on it. They use it for commercial buildings and residential buildings, and so the question is, maybe we should just use that. And it allows a lot of configurations. Many of those are commercial. Most of them are driven by mechanical flows. And so what you do is you specify flows that are going between zones, and then it tells you where, how contaminants might be transporting through that building. So that's exactly what we want to do, right? Except getting back to this, for a model of a home, we need to say how much air is coming in and how much air is going out, and it's kind of the same zone. And so when I dove into the NIST model, you can do that. You can define a zone that is like a home where flow is going in and going out, but the model asks you to specify one of the things that we really don't know. It asks you to put in the neutral level, which, like, if I knew that, right, then I would know how to model everything. And so, or at least I would know how to model that one zone much better than I do. And so for our particular case, the NIST model seems to need the exact kind of guidance we're providing, but it doesn't give the guidance that I want, if that makes sense. And so right now I'm fiddling with this simple model and not using the NIST model, hoping that what we do here can maybe provide an update to that type of zone. And yeah, Paul, I'm curious about your thoughts on this, if you have any additions, or if because you might have used CONTAM in a different kind of way that I'm missing here.
Really, I mean, the CONTAM, if you're trying to understand flows, say, between the house and the attic or in a garage, it can be helpful, or multifamily can be helpful, but trying to do it with a different flows within a single zone is certainly not its strength. I also just say, in case people don't know what neutral level is, that's where you go from air coming in to air going out up the wall of a house.
Right. So the house kind of balances itself, and it seeks its own neutral level to make the flow in equal the flow out. That depends on how the pressures are distributed, where the leaks are, and so on. And that's one of the things that is handled. I think I'm saying this here. Oh no. Oh, okay. One of my slides disappeared. That's why we went straight to the NIST slide. So one of the benefits provided by what's called infiltration models, and so you may hear of a model we refer to as the LBNL model. There's another one called the AIM model. These are simple one zone models that try to do that balancing, determine how much flow is in or out depending on the conditions, and then determine the magnitude of the flow. And so, yeah, so they're kind of the in between. Okay, so what I'm going to show you next is some of the what if cases that we can do with a single model, and that single model also, or single zone model, also could include air handlers as a separate zone, or air purifiers as a separate zone. And all I'm doing here is exploring some of the cases, particularly that Christian might be thinking about with regard to anticipation. I will preface this by saying that I think as soon as I show these things, people are going to say, well, what about this and what about that? I'm happy to take those what abouts. I didn't do all of them. I'm happy to explore them. And so maybe we would just want to have a working session where we explore them, but I may not be able to answer your questions here. And the model may not be quite suitable yet, so it may need some nudging. But from hearing all the what abouts is how we'll go forward to having a model that's useful for a lot of people. So for those of you who are not accustomed to thinking about air exchange rates, just a quick overview. it's common to present them in inverse hours or hours to the -1. So 1 air change per hour means that the flow into the house and the flow out of the house in 1 hour is the whole volume of the house. Now, this does not mean that all the air is refreshed, because as the flow is coming in, it mixes. And so you don't replace it all. It just means that the flow has been the whole volume of the house. So then a more common air change rate is something like 1/3, 0.33 air change rates. So the flow in and out in 1 hour is 1/3 of the volume of the house. So it's a way to think about how tight or leaky a house is, independent of its volume.
Tammy, can I ask a
Yeah.
quick question?
Yeah.
When you talk about the pollutants, are you talking about outside pollutants, inside pollutants, or both?
So, well, that's what we're going to explore. I'm going to show you both. So the model can do both pollutants coming in from outdoors or pollutants that are generated indoors, and how long does it take to remove them? And that's probably one of the trade-offs we'll be thinking of. So the first thing I'm going to show you is the effect of an outdoor concentration spike. So this, to answer your question, Lori, is an outdoor pollutant. And what I did was I made a 10-minute spike, a spike that was continuous but lasted only 10 minutes, one that lasted 30 minutes, and one that lasted an hour. That spike begins, right, it doesn't begin at time 0, but it begins a little before you see the concentration in the house rising. I should have marked that on here, but I didn't. And so what happens is it takes a little while for it to mix into the house, for the polluted air to be drawn in. And the longer that spike goes on outdoors, the higher the concentration rises. And then when that spike is over, I just made the outdoor concentration return to 0. And then fresh air is coming into the house, replacing that polluted air. So you see the concentration decline. So is that, yeah, is that clear? And is it clear why the 3 curves differ? That the house was just intaking polluted air for longer. And the units on here is just the percentage of the outdoor concentration. And so it never gets up to the full outdoor concentration because it doesn't have time to fully replace the house's air with the polluted air. So this is a house at 1/3 air changes per hour, 0.33. And the next 2 things I'm going to do are compare it with a tighter house and a leakier house. So the figure I just showed you is over on the left, and now there's a house at 0.8 air changes per hour. So it's a leakier house over on the right. So you can see that compare the concentration axes, the leakier house gets more in it because it's drawing in air faster, but then it also clears out faster because, so people are exposed to higher concentrations that persists for a shorter period of time. And, oh, my tight house disappeared too. Dang it. Okay, lots of my slides have disappeared. But I can make them again, because once the model works, you can make lots of figures. It's making the model work that's not good. Okay, so I have not explored air purifiers yet, but what I did was I turned on an air handler that had a MERV 13 filter. Filter ratings go from, I don't know, something like low to 15 or so, and the higher the number, the better the filter is. 13 is pretty high for a furnace filter, but those filters are still not very good at removing the small particles that make up wildfire smoke. So the efficiency of this filter for this size is about it's about half. It removes about half the pollutants every time it passes through. So this is the same house And as soon as you sense the indoor concentration, which I defined as something like 0.05, the air handler goes on. And so this is a question of like, does it actually make it better if you just turn on the air handler and you have a filter? And it does not rise to as high a level, and it also clears out the air faster. And then I'm going to take away the left-hand graph. And this may not be a fair comparison, but my question was, well, what if we turn it on a little bit earlier, like we could sense it 15 minutes earlier by sensing outside, like Christian is doing. And if you turn it off as soon as the outdoor concentration rises, you see a little bit of a decrease, but you still do get a pretty high peak. So this is not saying that the anticipation doesn't work. It's saying it's not very good in this case. And so what do we need to do to reduce it? So you can see that it has an influence, but it's not a very big influence. And so if you push that filtering on and start cleaning the air, even as it's coming in, you're really only, you're cleaning a little bit more air, but not much more. And that's why it doesn't make a huge difference yet. So those are my what ifs so far, but just so you know, this tool is sort of now available so we can explore questions of, okay, what if we did this, or what if our filtration efficiency was better, or what if we had a higher flow? I feel like my air handler was pretty big because I was doing, it's a small house, and I was running the air handler at what would be 2 air changes an hour. And I felt like that was high, but I'm not sure. Okay, any questions so far?
I have a really quick question. Sorry, this might be really basic and I might have just missed it, but is this simulated or like observed from an experiment?
No, it's totally simulated.
Okay, that's what I thought, but then I started to question it. Thank you.
Yeah. So this is the simple model is just to explore what if cases. Like, would this, before we go build it, would this make a difference?
Thanks, that makes sense.
Yeah, Tami, I think this is great. Probably more details than we want to get into right now. Carson and I are working on some similar ones, so it'd be good to do some cross-pollination with our kind of assumption cases, just to make sure our 2 models are agreeing well. If it'd be useful at some point, I'd be happy to share some of the outdoor concentrations that we're using that aren't spikes
Yeah.
when you get to that point. Just a little teaser, one of the things that we've been finding most interesting so far is even if we only start at when we first see the rise, what you're seeing here, the difference of that versus if you started the air handler or the cleaning process at concentrations either outdoors or indoors that guidelines currently say this is when you should take action, are 2 massively different outcomes. Does that make sense?
Okay. It would be good to put those all together.
Yeah.
Cool.
Happy to chat offline about how to maybe do that most efficiently.
Cool.
The
And then
long and short is what we're seeing so far is maybe guidance comes too late, not the ability to detect that the anticipatory may be most beneficial before the concentrations are high, but we don't actually need to predict potentially before we see a rise. So like CDPHE only tells people to clean their air when it's already past the point that you can do the best,
right,
the
yeah.
best gains.
Yeah, okay. Okay, and I have a like a really simple shape, like just a square shape now, but it can take minute by minute inputs if you have outdoor concentrations. Okay, so the other thing that I have been working on, and this has fussed me, is to Erica's question, what want to do is get this model implemented with the measured pressure data, which is less straightforward. And so what I'm going to show you is totally preliminary, and I have not I'm completely unconfident in my interpretation or use of measured pressure data, but that's going to be an ongoing process because that's one of the new things about this project. So just to remind you, blower door tests give a relationship for flow at constant pressure. That looks like this. You get a coefficient and you get an exponent. But the blower door differs from operating conditions because the blower door has a constant indoor-outdoor pressure difference. And in real operation, that pressure difference between indoor-outdoor is going to vary with height, temperature difference, wind direction, and so on. So on every piece of the building, you can imagine a slightly different pressure difference. So the blower door has one-dimensional flow. The operating conditions flows can be inward or outward depending on location. And the game is to take the measurement you get from a blower door that is under very simplified conditions and then use it to project what would happen knowing something about the leakage of the home under regular conditions. Okay, so, and then infiltration models bridge the gap because they estimate leak location relative to where those pressure differences are, and then they infer a flow through a bunch of leaks. So what we're hoping to do in this process, the thing we're adding is measure that pressure difference under real conditions. Then we can use it to predict the flow, then plug that into the flow matrix, and then predict the concentration. So the results I showed you before are the flow matrix versus concentration. But what we haven't done is connect our pressure measurements, which we showed you, to flow predictions that then go into the model. And I will tell you, this is not right yet, but I want to show you a couple of things. So it's pretty difficult to actually attribute a pressure to, like, this part of the pressure is from the wind and this part is from the buoyancy difference or the stack. And so I'm not going to try to do that. I'm just going to compare 2 days, one when there was a lot of wind and one when there was almost no wind. And so we're going to look at the model behavior of flow during those 2 days. So this is where all the uncertainty is. Using our 3 delta pressures, here is my currently very bad estimate of infiltration. So day 1 has all the wind, and you can see it's jumpy, and the infiltration may rise when the wind is high. And on day 2, it's more flat, and that's what you would expect from something that isn't as jumpy as wind. The real uncertainties here is you measure pressure on a wall and you don't know how many leaks or what area of the wall that corresponds to. So the infiltration models attempt to project that, like, okay, if this pressure is here, then this whole wall is exposed to it, or only part of the wall. And so that is where all the questionability arises. Now, to be fair, in the infiltration models, they assume where the pressures are and none are measured. And so we're at least adding pressure measurements that can tell us whether the model's assumptions are correct. So what does this do to what you would expect for an air or for pollutants in a home? So what I'm going to show you next is I've created an indoor source that is constant, just so I don't get confused. It's constant all the time. And I allow my predicted infiltration to remove that concentration. So if my infiltration goes up, you're going to see the concentration go down because fresh air is coming into the house more quickly. So here it is. Up on top is the predicted infiltration and the strong wind day you can see in the middle of the day as the wind infiltration or the wind driven infiltration peaks, the concentration in the home goes down. Now, I picked one of the very windiest days. And so you can see that there's a pretty significant effect of the wind on infiltration, but this is like 1 out of 5 days during 6 months. And then the other day where there's hardly any wind, you can see that the concentration is remaining fairly constant. And then in the later in the afternoon, it goes down a bit and the concentration goes up. And again, I've just faked out a constant source. Ellison, and people can jump in. I may not see your hands, but go ahead, Ellison.
That concentration is what you calculate from the infiltration factor you're estimating, is that right?
Correct. Yeah.
Okay, yeah, that's want to make sure I understood.
Yeah. So there's no measured infiltration yet. I'll talk about that in a little bit. But the 2 points I want you to notice here, even though we're not yet confident in our infiltration estimates, is that major changes do appear in the concentration in the home.
Mhm.
And one thing I was suspecting, and is borne out by the model, that the noisy pressures that are introduced by the wind, you don't really need to know all of those, because the house volume is changing relatively slowly. It acts as a buffer. And so that wind pressure, even though it's really noisy, you don't see that noise in the concentration in the home.
Yep.
And so you need to know wind average. I've got I've been measuring the 2 taps on the same wall, and they can be quite different for when it's windy. And so then I started wondering, like how representative is each tap? And I think you just mostly need an average over that period. These are 1 minute data, by the way. And so the measured data, the measured pressures are real, but the concentrations are inferred from the model. Okay, so the last thing I want to say, I don't have another slide, but the goal of the tracer gas measurements is going to be going backwards from a constant injection of tracer gas. So you'll see a change in concentration, and then theoretically you can back out what the total infiltration is during that time. And so then we can confirm whether the infiltration model that we have is accurate. So what you've seen is going forward. Then when we start with the tracer gas, we're going to go backward through that process. Okay, that's all I have. Any questions?
Let me ask a question from a non-scientific point of view. Okay, trying to put this together. So you're making this model as part of the paper? Is this part of your whole thing that you're presenting to as part of this project? You're developing this model upon which you're going to design your instrument that's going to filter, and once you get that all set up and running about how it's supposed to act, the model is sound, the instrument is sound, then from there are you teasing out the behavior of the people in the house? Because
No, we're not.
because I thought the whole thing was about the behavior of the people. So am I not understanding this at all? I mean, I thought, that the model, then we're developing the mechanical process, instrumentation. And then once we get that about how it should work, then the variables will be more related to the people's behavior in the houses.
So I think the specific things that we're identifying about the people in the house relate to how the mechanical systems behave. This is just a physical model, right? So we can only tease out what's happening physically. Now, the people have a role in determining what is happening physically.
Mhm.
So, for example, if they need to turn on an air cleaner and they do not, then you would not see a decrease in particle concentration. But I think that I'm going to try to answer your question first, and then I'm going to say something else. So there are things that people do that will be visible in the model, but making the inferences from what you see in the home is actually quite indirect. And so Erica, I think, is going to have some measures that more closely observe the people, like, did they run the air handler or the air cleaner? It's much easier to determine that from measuring the current to the air cleaner than it is from measuring whether the concentration in the home decreases and trying to figure out why. So this is this may not be able to be traced back completely to what the people are doing, even though that is a
That would be
component.
big factor, right? I mean, because, I mean, maybe this is like a two-pronged approach, right? Erica figures out a more direct way to measure that behavior along with this scientific model and the mechanical part, right? So it's how to marry that all together.
Yeah. So it's like a 6-pronged approach, really. So the other thing I want to say is that there's a few really important parts in this project. One is the behavior of the environment or the house, and I consider the house part of the environment in this context. The behavior of the people, and then the behavior of the pollution. And so we don't know how people behave. We also are kind of short on understanding how houses behave. And so when you decide how to mitigate something, you're making assumption about the people, but you're also making assumptions about how the house behaves. And so part of the goal of this project is to fill in information about how the house behaves and give us a better handle on it, so that the measures we prescribe would be effective for that house. Now, they also have to be effective for those people, but if those people are told to do something and it wouldn't be effective in that house because it's too leaky or too tight or whatever, then they would also be wasting their time. So there's a part of it where we're filling in understanding of how homes work.
Okay.
I think what we see right now, Lori, is there's some information on outdoor concentrations were this much and indoor concentrations were this much. Well, that could be because the house was leaky. It could be because people opened their windows. It could be because they weren't using mitigation technology, but we don't know. And without having a little more understanding of what leads to that relationship, we can't identify which thing to nudge. Okay, so I don't have anything else. Looks like nobody else has anything else either.
I had something unrelated that was what I asked you earlier, that maybe Christian and I could just stay on for the remaining time. I had a question for him about sensor.
Okay. Yeah, so in summary, the reason I'm bringing this here is not so much to say I did some work and here are the results. I don't actually consider these results. I consider these a tool so that people can ask questions and especially so we can start trying to merge what we're learning about pressures with what we should be seeing about house flow. And so when in the future, when you see this sort of coupling between measured pressures and predicted infiltration, you understand where it came from. You know, and likewise, if you asked a question, well, under those conditions, would it be, is it effective to turn on the air cleaner or to run a bath fan? Then we can quickly answer those questions, not with measurements, still speculative, but with some kind of direction. And Christian, it sounds like you have ways of answering that too.
Tammy, I did a quick calculation. You had that 2 air changes per hour, which I think was recirculation with the air handler, right?
It is, yeah.
Yeah, and that's actually a relatively low number.
Oh, okay.
Yeah, if you went up to 3 to 4, that would be probably more like what an air handler can do. A typical air handler in a typical size house.
Okay. Yeah, that's the sort of thing I need help with.
Yeah, I just did 800 CFM air handler in a 1,700 square foot house. And that worked out to be about 3.5. So 3 to
Okay.
4 would be good.
I think some kind of guidance on sizing flow rates, like what you typically find in a house. And it sounds like that would be how it was sized. And then for a heating application, then you would not, it would only be running every 10 or 15 minutes or so. But then if you had,
yeah, but only you're running like a quarter of the time, but if you're using it to clean the air, you could put it on all the time.
right,
Which oftentimes a fan only mode is at a lower speed, which might take you back down to that too. But there are also plenty of fans that are only single speed or maybe 2 speed, one for heating, one for cooling, and the cooling would be larger. Typically, cooling is usually going to be another 25 to 50% larger than the heating speed.
okay. So that when you say speed, that's just the capacity that the fan has, right?
Right.
And so it could be used at that speed for cleaning.
Yes,
It
it could.
doesn't have to know if it's heating or cooling at that time because it wouldn't be either one.
Right. I mean, so in the wiring of a furnace or of a thermostat, you can have different settings for, is it the cooling speed, the heating speed, the fan only speed, but you don't have to have them be different. You could have the fan only speed also be the heating speed or the cooling speed.
I see. Yeah, and it's the fan only that you would use for a cleaning
That's right.
application.
That's
Yeah, and I'm
right.
not sure that running it through this with a MERV 13 filter is the most efficient either, but that's just what I did because it had MERV 13s in the, in the
Yeah.
database efficiency.
Last rate 62.2 gives you a credit on your ventilation rate, your required ventilation rate, if you do this, recirculate through a MERV 13.
Really?
I don't
Oh.
agree with it. I don't agree with it, but it's actually in the standard.
I see.
I will say in 18 years of being on that standard committee, I think it's the stupidest thing we've ever done. But
Okay, well, if I can provide any model results to support your case, just let me know. Yeah, anyway, and then we can do multiple zones, which I didn't show here, but just like what would be the effect of a separated zone like Ellison is talking about, like we're talking about in the Epic homes. So under what conditions would we expect differences in concentration? Yeah, okay, so that's it. Thank you, everyone.
Yeah, thank you.
Have a good weekend.
Bye.
Bye.
Did Ellison want us to stay on, or I got confused by that?
Yeah, I thought she did. I'm gonna stop recording. Maybe because we went over the end.